Okay.
Okay, so thank you for still being here. I will grab my syllabus. Now, I covered a little bit the historic and the philosophical and the whatever part of quantum mechanics. Let me now come to the formalism. And please interrupt me if you have questions, because the formalism can get a little bit dense, and I'm happy to answer your questions if that is necessary. I will relate also to quantum logical entities whenever this is appropriate. So let's just start with the Hilbert space. Now, Hilbert space is basically modulo the completeness of this space is basically a vector space endowed with a scalar product. And there is a notational issue which shies mostly computer scientists away. This is and if you look into the book of David Mermin, he has an Oxford University Press book, Quantum Computer Science. He has solved this issue, in my opinion, brilliantly, because he introduced vectors, very particular vectors, already in the bracket notation of Dirac. What I'm going to tell you is mostly a notational issue. There's nothing deep in it. But usually, I don't know how vectors are introduced in the Chilean system, but in the Austrian system, vectors are introduced with this little arrow here. Yeah, the same. So quantum physicists, in order to confuse everybody, have introduced another notation. They call this A. Okay? So once you have digested that, you are well into understanding quantum mechanics, because you understand that this is a vector. It's nothing else. And I mean, where does this come from? This comes from this notion of this scalar product. And let's make it simple, and let's stay with real numbers only, and real valued vectors only, whose components are real. Yeah. For all practical purposes, in our case, we only need real numbers and not complex numbers. And then a scalar product is linear in those coordinates. If we are in Rn, let's say, if this is, and this is then element, this is then a number, and it's linear means, I just write the definition here, is that alpha A plus beta B C equals alpha A plus beta B, and that C equals alpha AC plus beta BC, and also in the second argument, and so on and so forth. So there exist certain rules which the scalar product should obey. This is one, linearity is one of those rules. I should obey the associative law, and for all of you who would like to know more about the formalism, I may advise you to read my manuscript. Now I have a. Is there Thomas? Is there any way of getting?
Yes.
Here. Okay. So this is available from my web page. Where's the web page? The web page is, just a second.
Oh, but we make it available on the course website.
Yes. So
it's available on the course website.
Yeah, it's if you Google me, my name, and you see on the web page the course on Masters of Mathematical Physics, and this is what I teach every year at the University of Technology in Vienna, and this contains, let's say, here contains in English contains the feature for the vector spaces, because a vector space is basically a collection of vectors. Let's see. Where's the scalar product? No. So let me begin to tell you that the vector space is a collection of vectors, and you have two basic operations on that space. One is the addition of vectors. And with respect to the addition of vectors, the vector space is closed. So if you add two vectors, if you add an arbitrary vector A and an arbitrary vector B, you get a vector C, which is again part of, if you denote the Hilbert space by R, which is again part of this. So it's closed. Yeah? And the same with multiplication with a scalar. Let's say if you have alpha A, if this is an element of H, then this is also an element of H. So it's closed with respect to addition of vectors and multiplication with scalars. And this is, by the way, already a quantum feature. If you identify this with pure states, if you identify vectors with pure states, is already a feature of quantum parallelism. That is, if you add two states, let's say two classical states, 0 and 1, yes, true or false, you again have, in classical physics, this has no other meaning than these two states. But if you identify in quantum mechanics these classical states with two vectors, then addition of those vectors makes sense. Makes again a vector. Makes again a pure state. And this is the basis of quantum parallelism, because you can add a lot of vectors, as many as you want, and push it through some processor. Now, this, as I said in the last lecture, the scalar product is meant to create scalars out of vectors, and this is what you can actually relate to when you talk about measurement frequencies, because this, the absolute square of this, or the square of this, if you stay in real Hilbert space, is just a measure of the probability if the vector is normalized. Now, I will only talk about normalized vectors. When is a vector normalized? A vector is normalized if the norm is a real quotation, isn't it? The norm is the square root of the scalar product of the vector with itself. positive square root. Yeah? If the norm equals 1, then you have, then R is said to be normalized. So far, okay? Now, of course, addition of that of two normalized vectors, if those are non-zero and so on, the resulting vector, in order to be normalized, has to be normalized again. Yeah.
Only finite sums? Only finite sums?
Well, this is again a question. I mean, the answer is no. You can have as many as also infinite sums. The question is if there is any operational meaning to that. Yeah. But let's say we will, in this series of lectures, only be dealing with finite sums and only be dealing with, as far as I can imagine now, and only be dealing with finite dimensional vector spaces. The dimension of a vector space is another important property. The dimension of a vector space is the number of maximal linear independent vectors. Now, what is a group or a set of independent vectors? A set of independent vectors consists of vectors such that no one vector is a linear combination of the others. So A, B, and C is not linear independent because C is just can be written in terms of the others. And let's say in 2D, a typical example in 2D would be the vectors spanning this Cartesian basis. Yeah? So if you add another one, this can be expressed in terms of the other two. And hence these three vectors are no longer independent, but these two, or also this one, are. Yeah? Okay? Yeah?
Yeah, regarding the dimension of the Hilbert space.
It's the maximal number. This is an additional feature. You know, you can have a three-dimensional vector space, two independent vectors, but this is not. This doesn't characterize the dimension. It's the maximal number.
Yeah. But for example, the case of a particle in a box, then you have a infinite number of eigenstates. So yes, the dimension of the Hilbert space of this problem is infinite, right?
Yes, but I will not talk about this case.
Okay.
Because all these, you know, in order to realize them, you need a lot of energy.
Yeah.
Okay.
Right.
And I'm not worrying about this. I'm just happy with. Actually, most of the time I will be talking about 3D.
Right.
And do you know why 3? Because this is the basis of the Gleason proof and also of the Cauchy-Specker proof. That in 3D, in 2D, you just have two vectors and that's it. And if you and this generates, so these maximal sets of mutual independent vectors, they form a so-called basis. A basis. Now, this is for the most common is the Cartesian basis, but you can have, let's say, rotated basis as well. You know, so if this is 1, 0, this is 0, 1. So this is 1 over square root of 2, 1, 1. And this is 1 over square root of 2 minus 1, 1. Okay? So they cannot connect. They have no common, in 2D, they have no common vector, in principle, in 2D. They are decaying, they are disjoint. However, in 3D, I hope I can make it clear with my hand. In 3D, you grab this hand and you rotate it, you can have a connect. And this is what Gleason calls an intertwining set of bases. Yeah? And this intertwine makes it possible to create structures which say one in 3D with one element in common. When they have two elements in common, they're the same anyway. Yeah? In 4D, they can have non-trivially two in common, but let's stay with 3. So basically, let's say the Cauchy-Becker theorem consists of a construction of a series of vectors which are intertwined. I call this a quantum shroud. And this can only happen from dimension 3 onwards. In dimension 2, it's trivial. I was once in Prague, and I was giving a talk on automaton logic, and I said, well, this could mimic dimension 2, which is totally realistic because dimension 2, it spins the state measurements of neutrons or electrons, So people would like that in physics. It's dimension 2. And they were just laughing at me and said, that's trivial, because they're decaying. They have nothing in common.
Sorry, which is the name? Intertwine?
Intertwine. Yeah, that's the terminology of Gleason. Gleason is the person who proved a theorem that nobody understood, and Bell actually started his investigation because I believe, probably this apocryphal, he wanted to understand the Gleason paper. Gleason out of, there was the McKay, Princeton, I believe, or in Harvard, this I don't know. Some of those Ivy League institutions in America, they heard from Neumann and Birkhoff, They were the creator of quantum logic. This is a centennial paper kicking off. This was the kickoff of quantum logic. And McKay, who was a mathematician, looked at the formalism and wrote a review. And Gleason got hold of this, and he, out of thin air, produced a fabulous theorem, which was very involved. Totally unexpected. He basically derived the Born rule out of very simple assumptions. The Born rule is the rule of quantum probabilities. That in order to get to a probability, if you base everything on vectors and so on, you can have only one form given the assumptions. Now the assumption is a very simple assumption. They wouldn't tell you that it is so simple, but it is very simple. It says everything that is co-measurable has to behave classically. Yeah? So basically, Gleason isolated the classical parts and in some way rearranged them together. The classical parts of what can be constructed out of the vector, and rearranged them and got the quantum probabilities. Now, I have not understood the Gleason paper. Pitofsky has a very, he tries to understand it and published a journal mathematical physics article about this. 3D. There exists also, of course, Dwojensky has a paper of Gleason. And there's an attempt to understand Gleason's theorem from dimension 3 onwards, including up dimension n and so on. Just like we parameterize the SO2 and SU2 and so on, or SOM by building subrotations in subspaces. So the the gist of this theorem is, let me tell you this just from the start, and this makes the quantum probabilities also this. You know, in quantum mechanics, I should say this. In quantum mechanics, you identify this with a pure state. And in quantum logic, you identify this with a proposition, which can be true or false. Now, why is that so? Because, the pure state, and this should be normalized, yeah? You assume that you have an A such that the norm of this is 1. And then you can construct, from this you can construct the projector by the exterior product, like this. This would give you a matrix that has idempotence. Because if you square that, idempotence means that this is equal to A. Now I'm talking really probably something confusing because you haven't heard this. But basically this is the beauty of the Dirac formalism. Here you have the A, and then you have this again, A. So you get rid of the bracket, of one of those brackets. And you have A here, if this is normalized, this is 1, and you end up again with this one. Yeah? So, what kind of construction is this? Usually one thinks of a vector in terms of the coordinates. Coordinates with respect to a particular basis. Yeah? So one would say that, for instance, x, the vector x, would be the coordinate x1 with respect to the basis e1 and e2. And if you identify this with 1, 0, and this with 0, 1, which makes it with the Euclidean product, just a second, with the Euclidean product as a Cartesian basis, then you identify this with x1 and x2.
Do you have a definition, a simple definition of what it is a pure state?
Yes. The pure state formally is a vector. Is that simple for you? It's a normalized vector.
Yeah, but not necessarily if the verse of the is not the
Exactly.
not necessary. It's
Not necessary. No,
yeah,
you can have the following vector, and this is part of Schrödinger's confusion. You know, this is the cat paradox. You can have dead and alive at the same time. So, if this is the alive cat, I like cats. I don't like dogs so much, but I like cats. The cat likes food, and this is the dead cat, real cat. You know, you can have it both ways. You can have, of course, you have to normalize this. But you can have a live cat and a dead cat. At the same time, it coexists. Now, imagine you coexisting dead and alive at the same time. I think that's the gist of Schrödinger's argument. But Schrödinger, throughout his entire career, throughout his entire lifespan, struggled with this. He went then to Dublin, you know, came back to Vienna, luckily ever after, but before he gave the Dublin seminars in the 50s, Schrödinger Dublin seminar, and he was saying, we are all getting, because of this feature, we are all getting quantum jelly. I mean, in the north you have a lot of jellyfish on your shores. You know what I mean, you know? Everything is jelly. Yeah, and we are without measurement, he says, and how do we get measurement? This is another issue.
So a pure state is a vector,
Yes.
but not necessarily is a base.
It's not necessary that it is.
It's the base. If one vector the base.
You know. So
But
okay. Let me say this. What you consider as basis may be very evident to you, but from a formal point of view, it's totally arbitrary. As long as this thing is a collection of mutually independent maximal vectors, maximal set of mutually independent vectors, it's fine. You know. Usually people say this. You shouldn't stick too much with basis ontology. If you shouldn't stick too much with Cartesian basis. Of course, everybody is using Cartesian basis. You know, but the last chapter of this book was curved linear coordinates. I struggled a lot doing curved linear coordinates. And I think the students will not like it because it's too complicated. But you can do curved linear coordinates, no problem. But so you can say, well, the natural state for a cat is dead and alive anyway. So then the paradox goes away. This depends on your basis. From a mathematical viewpoint, if you have a vector space, any basis, and you define basis by a mutual, maximal set of mutual independent vectors, is okay. Now, usually you like to have orthogonal vectors. Now, orthogonal, what does that mean? For orthogonal, this is another reason why you need a scalar product. Because with the scalar product, you can define orthogonality. You say, if the scalar product of two non-zero vectors is 0, then I call these vectors orthogonal. Yeah, it's another reason why we need. So one of the reasons is to get quantum probabilities or frequencies in prediction, and the other way is to define orthogonality or collinearity. Yeah. By the way, you can transform the coordinates. It's like once we settle on what frame. Let's say from here to Vienna, it's approximately 1 million steps, you know. And then I use another base, which half of the size of the base vector. And of course, the coordinates transform contra variable. So if I vary, I need 2,000 steps if I half my size, you know. So, or if I extend it to 2 meters, I only need 500. That's purely conventional. Once you set the scale, the coordinates transform in tensor geometric terms. It's called contravariante. Yeah? That's a term usually you only hear in Minkowski geometry of relativity theory, but it's true everywhere. The contravariate with variations of the passes, those components. Because at the end, you have to describe a physical way, you know, a physical way of going from Santiago to Vienna. And you can conventionalize your scales, but then you have to adapt your coordinates. And you can not only, you know, just shrink or expand your scale, you can also tilt it or whatever. But usually, to be on the safe side, we will use only finite dimensional vector space. We will only use Cartesian coordinates. And we will stay within probably 4, because there's a very short proof of because we take a theorem with dimensions 4. Developed by some Madrid guys. One of them is now in Sevilla. Also, for instance, if a particle passes a double slit, let's say if a particle the funny thing with the double slit is the following. you know, you have this kind of thing in the double slit again, you know, passes through one slit, passes through the other, or through both. Yeah, the double slit is usually described in a way that doesn't really exemplify the interesting part of it, because let's say what happens if you have a source here, and here you have this. Usually one says, well, if I don't close the slit, you have interference pattern here like this. This, and then you say, well, this is a wave, basically, so this is a Materiewelle. But there exist experiments and stimulated from neutron interferometry. This is one of the nice experiments of Seilinger that he quoted for. In neutron optics, unlike in photonics, like around here, they are used to statistics which are humiliating. You know? One particle in a week. No, I'm joking now. You know? With photons, you have so many, but with neutrons, the flux is not very high. And if the interesting thing is, what happens if you reduce the flux such that you can be quite sure, for all practical purposes. You know, famous paper for all practical purposes, this is the paper, late paper by the late Bell, from Bell. It's not how to teach relativity. This is another very interesting paper, very old Fitzgerald. But I'm not talking about relativities, although I would like. It's also very interesting. It's about against measurement. The paper is called Against Measurement. And his criterion of the popularity of the interpretation of quantum mechanics is in terms of how many books are stolen from the CERN library, which is good. I mean, when I came back from Vienna, I found all the books stolen in the Berkeley library, in the Vienna library. You know, it was like Eldorado for me, because all those books were there. You know, in Berkeley you had to start because they were stolen. Anyway, so I'm not going to talk about this. This will be the time. If the source is so weak that you can be quite sure that for all practical purposes only one quant will be in those interferometer at the time. You know, you will not observe immediately this, but you will observe a click here, and there a click, and there a click, and then a click here, and then a click here. So the clicks will kind of pile up to give this pattern. There will be regions where there are less clicks in the photographic illusion. So you kind of have to assume, and this is unlike yesterday, wave theory, that the single particle interferes with itself. So you might think, how would you feel going through a double slit? You know, you kind of, this is like the Senko line, you know, Asian philosophy. You go through I mean, I'm not into this. You know? I'm just saying that this is the cat's paradox, basically. You know, and this is what Schrödinger struggled with, because he said, if it is true that we are in a coherent superposition, then we might get totally jellified, because the jellification is like the doubling seminars. We might get totally jellified, and we might not. How is it that the world is so unique, so concrete to experience? This is Schrödinger's question. He has no answer. He has no answer.
This experiment with neutrons is by Tonomura?
No, this is Panzani. You know, I know something about this paper which I should not tell you. It's totally okay, but well, it was accepted in 2 journals, let's say this. And of course, but of the same society, now I say it. And of course, Salinger decided to have it in the Reginald Fuchs. It's a Reginald Fuchs paper a long time ago in the 80s. It's a very interesting measurement because it's simple. You know? And this is what the quantum optics community didn't realize, and this is what made it so advantage was to come from the neutron society, because the optics guys, they had too many photons, they were spoiled. But those were really difficult with small numbers and small statistics and to wait. Okay, so really, I think this is one of the most important features in quantum parallelism is based on that you can have, if you combine, let's say, I was quoting Mervin. Mervin would identify this here with the bit 0 state, and this here with the classical bit 1 state. Yeah? So the 0 state has 1, 0, and the 1 state has 0, 1. By the way, Mervin was kind enough to give his almost entire lecture on the internet. So if you type in David Mervin, go to his page, he has a page where the book is basically presented, but not in the form of a book. It's in form of a chapter. But it's okay. I mean, the Russians have it also for download. This is not, I don't think it's the Russians. I think it's the Germans pretending to be Russians. Anyway, so let's not talk about this. You know, and of course with this advent everything changed because you don't have to worry about excess of papers anymore. You know, you just get it by the DOE once you get the DOE. Now, and there's now an initiative of the European community and of the finance agencies. Like, I think FWO should be also in one. I've not heard about this. I was wrong with FWO, but also the Austrian Science Agency definitely is in that. They said, if it's publicly financed, then it should be publicly available, the research. You know? This is, I think, totally correct. Totally correct. And Nielsen went into that kind of policy. Nielsen, there's a famous book, so I would recommend this book to you. I would recommend vector space theory, first chapter of my book, and I would recommend as a standard reference the Nielsen Huang book, and made it into the 10th anniversary edition, Oxford University Press. Also, I don't know how it's called. And now, I think it's Huang.
Yeah, I think it's G over there.
G?
No.
So I'm never sure about this. I'm sorry. I'm really happy that I can write down my name, but the names are not very reliable. But it's a standard reference. Very nice, very well written, very formal. So, if you have this, you can have, of course, all states. Let's say you still remain in the real part. You can have this also. You can have 1 over square root because of normalization. 0 plus 1. So you can have an even mixture of zeros and ones. Okay? Why is this normalized? Because you have 1 over square root of 2 to the square, and then you have 0 plus 1 and 0 plus 1. And this gives you 1/2 times. I just do it now very slowly. 0, 0 plus 0, 1 plus all combinations. Yeah? 1, 0 plus 1, 1. Now, because of orthogonality, this is the Euclidean product. This is 0, this is 0, and because of the assumption that these are unit vectors, this is 1 and this is 1. So this is again 1/2. It's 1 over 2 times 2, that makes it 1. Yeah? So this guarantees the normalization. But you can have all kinds of mixtures, you know. And so the most general pure state. The most general pure state is, I write it down in this full glory, in terms of the Mermin 0 and 1, yeah, it's psi in 2D is alpha 0, alpha 0, 0, in terms of the Mermin nomenclature, plus alpha 1, 1. Such that, I mean, this is now true also for complex alphas, for complex vectors, such that alpha 0 squared plus alpha 1 squared equals to 1. That just guarantees that it's normalized. Yeah? And this you identify with 1, 0. And this you identify with 0, 1. So this is the most general state, and from here you see already the quantum parallelism, because you can have it both ways. But, of course, there's a trade-off. You have no access to this state directly. You cannot get a grip on it only if you measure it, and then measure it means you have to measure to form a scalar product and form a scalar. But then you kind of lose some information. So the idea of Gleason was, he says, if you have vectors, how can you at the same time and I should say the following. There exists a feature called complementarity. The complementarity means that you cannot measure certain propositions simultaneously such that both propositions are determined uniquely. But for this, I need the notion of a proposition. And I said already, a proposition is derived from a pure state such as this. Now, how is this actually formed, the exterior product? It's a kind of a direct product, such that, for instance, if you have 0 here, which is again 1, 0, you form such a thing here. Now this here is the so-called transposed or a Hermitian transpose of this. Now, if you are staying in the real Hilbert space, this is just a transpose, so this would mean it's a vector with these components. Yeah? Because the transposition just changes the orientation. Just a transposition of this 1 times 2 matrix gives a 2 times 1 matrix. So how does this look then? It's just like you have 1, 0 here, and then you have 1, 0 here, and I make it so, and then you form the product by just multiplying every component of this column vector with the row vector. So you say 1 times the row vector, 0 times the row vector. Okay? So this gives you 1 times 1 is 1, 1 times 0 is 0, 0 times 1 is 0, and 0 times 0 is 0. Okay? So this gives you a thing that, as I have proven before, should be idempotent. Idempotent means that this object, let's call it E, that the square of this object is identical. Now, I hope, do you know how to multiply atoms? I mean, for instance, this element, if you have 2 matrices, A, B, C, D, E, F, G, H, you form, this is again a matrix, which is the product of this row vector, the Euclidean product with this column vector. So you have A times E plus B times G. Yeah? And so on and so forth. So if you do that, to that one here, it's just again this one and that's it. It's a projector. But you can see that for all vectors which are unit vectors, you can see that this leads to an idempotent projector, and the idempotent projector. So the vector is identified with its pure state, and the idempotent projector is identified with the proposition that the particle is in this pure state. Okay? And the quantum probability, according to Gleason, this is the first 2 paragraphs of this paper, and you need not read any further. If you speak of pure states, most of the other part that's in the Gleason, most of the complicated parts is with mixed states, non-pure. What is a non-pure state? A non-pure state is a state where this is not idempotent. But it should be of trace class 1. Let's say this. Trace class 1 means that the trace of the matrix adds up to 1. So if you have a vector, how would you be able to get now I should introduce co-measurable things. Now, co-measurable things is defined in complementarity. Complementarity is defined in the following way. You have a so-called commutator, which is defined by A, B. This is defined by A times B minus B times A. Now, if you have two objects, and if those two objects, if AB equals 0, if this commutator is 0, you call them co-measuring. Else, you call them, is not equal 0, you call them complementary. AB complementary. Okay, this is a simple definition. Now let's use this 2D example here. Now for this your proposition here can be formalized, as I said, by 1, 0, 0, 1. And this, if you do the same, can be formalized by 0, 0, 0, 1. Okay? And you call this E1, and this you call E0. Now, what is E1? E1. That's trivially 0. So if you measure it twice, no problem. But what is E1, E0? Now this is also, this is E1, E0 minus E0, E1. And this is only, this is 0, and this is 0. And this is ultimately only true because these are orthogonal. If they were not orthogonal, it wouldn't be 0. So you can have orthogonal bases, and the orthogonal bases are characterized by all corresponding projectors formed by that basis vector commute that is correspond to co-measurable observables. And what is the reason for this? Or how is it formalized? Now, an orthogonal basis is usually the formalization of a situation where you have, let's say, two outcomes, and those outcomes are compatible. They are not complementary and can be co-measured. So if you have n outcomes, let's say an arbitrary beam splitter with n output ports and n input ports, those would correspond to a Cartesian basis, let's say, in n dimensions. Or to any other basis which consists of mutual, orthogonal, and normalized vectors. Just as this one. Yeah? So in a Stern-Gerlach spin state measurement, you have two outcomes. One up, one down. The one you call 0, the other you call 1. Or in a photon polarized linear polarization measurement, you have horizontal vertical. Yeah? This is a formalization. Now, if you have a state like this, and this is the Gleason argument, you can still measure what components, by multitude of measurements, what components are of these orthogonal vectors are in that vector. And Gleason said, well, you can, if this is psi, you can ask, well, given the psi, what is the 0 component? And given psi, what is the 1 component? And you surely will always measure either 0 and 1. So this has to add up to 1. Yeah? So, and how can you construct this? Is everything here is just unit vectors. It is the easy construction, second paragraph. You draw the orthogonal projection here, down there, and by the Pythagorean theorem, you identify this with ip0, ip0, and this square, square root, and this with square root of ip1, because this is of length 1 here. And the projections by the Pythagorean theorem, now the orthogonality is here, you get that the square root of this vector here, of the length here, of the length of this vector plus the square root of this vector is equal to 1.
It's always 1, no matter the angle?
If you take another autonomous system, let's say, if you take this one, if you align this, it's also true, because this component gives you 1 and this 0. Or, if you take a little bit rotated, always gives the orthogonal projection onto each other, always gives you 1. So, in a sense that an autonomous basis is a sort of probing instrument which gives you a view on the pure state. Yeah? And the idea is that you can measure, that these things are co-measurable, so there's classical mini-universes that are called contexts. You can co-measure those properties, and they all add always up to 1, no matter what. You know, because let's say you want it this way, this is arbitrary. You know, you can probe this psi with arbitrary autonomous systems. The square root of the length of this times plus the square root of the length of this will always be 1. Always. And this is a realization of the Kolmogorov axioms of probability theory for co-measurable properties. So you have it both ways. You have this is the fantastic idea that Gleason had. You have classical mini-universes among those things which you can co-measure, and you have a vector-based probability formalism, which gives you different probabilities than the classical ones among non-co-measurable. Because if you just look at this here, let's say if this is E1 prime or E0 prime, you have E0 prime psi. The square root of that will correspond to the probability given the state psi, the probability of this property, whatever that is. And this is here a scalar product. So it's non-classical, it's vector-based. It's a vector-based probability. And it assures that if these things are co-measurable, that is, if they are complementary, they just add up to 1. That's the beauty of the Gleason theorem, at least as I understand. But of course, it's only the first paragraph. So my understanding is only the first 2 paragraphs of Gleason. And I know that I would understand the entire. I would go to Pitofsky and read 3D or Turečensky, but I would forget it. because it's mixed. The question is, what is a mixed state? A mixed state is something that you lose information. You lose information of the vector. In a mixed state, yeah. This is different, and I hesitate to talk about mixed states because I don't believe in mixed states. I think they are epistemic only. They are not only. So how long am I going to? Yeah, I think we have half an hour. Now, mixed states, probably I should, yeah, mixed states are states which, I mean, it's easy to define it formally. Mixed states are such that they are not idempotent. No, sorry. Yeah, they are not idempotent. They are not idempotent. So they don't correspond to let's say, you cannot represent them by vectors. But what you could do, typically, but still the trace of a mixed state should still be 1. So, what is a typical example of a mixed state? Let me give you a typical example of a mixed state. It's just an identity matrix. 1, 1. And in order for that to be satisfied, you have this. So this is a mixed state. I shouldn't write E. I should rather write rho. Usually one writes rho for the quantum state. E is okay because mathematicians sometimes projection operators are like this. So now E squared, E squared. Yeah, so the sum, the trace, 1 plus 1 is 2 times 1 over 2 is 1, that's okay. But this one here is 1 over 4, and 1, 0, 0, 1 is, and 1, 0, 0, 1 is 1 over 4. The identity is equal to 1/2 of rho. Yeah? So this is a typically mixed state. I mean, you can of course construct a mixed state by, but this is not a unique way, by summing up projectors. Let's say you can write 1/2, say the E, the rho here is 1/2 over 1, 0, 0, 0 plus 0, 0, 0, 1. And here you get E1, E0, and here you get the E1. So 1/2 times E0 plus E1. This is a typical sum. Yeah? When you can write 0, physicists like to write that. Okay.
What's the physical meaning of the trace?
The physical meaning of the trace is that in Homogorodian terms, all things that you can co-measure add up to 1. That you exhaust all possibilities. Yeah? There's a click here or a click there, and it's normalized. It's a kind of normalization that in an ideal experiment there has to be some occurrence. Yeah, so the output, some output ports in a generalized beam split the files. It isn't the case that 2 file or 0 file if you enter one. So So the physical meaning is basically a kind of something happens. It doesn't say what exactly happens. If you have a state E0, then the zeros, the word associated with E0 happens.
So a mixed state, you usually are written by a summation of pure states.
Yes.
And you can have many pure states added up. You have a mixed state of any pure state.
Well, as long as these criteria are satisfied. And the mixed state also should be Hermitian.
Hermitian?
Yeah. Hermitian means that in real terms, that rho Hermitian conjugate or just a transposition in real vectors is theorizable. Because if you do the spectral theory, you can see that this can be decomposed into projection operators, into the spectral sum. Anyway, so the question is now. The question is, how do you get a mixed state from a pure? I mean, how to get a pure state is pretty easy. You throw your particle onto a beam splitter. A beam splitter is something that would divert the components into the ones you had in mind, and filter out the ones you don't like. What remains is the pure state. Now you got the pure state. The question is how do you make a mixed state out of a pure state? And that, according to Schrödinger, is a problem because actually, due to von Neumann, this was due to von Neumann and Everett editing his Ref-Mod-Fus article also. There exist basically two processes in quantum mechanics, and now we come to the process thing. Now, but let me tentatively answer the question how to get from a mixed state to pure state. And this is via so-called partial traces. That is, you kind of trace out one particle and such that you pretend not to know what its state is of an entangled pair. I will shortly tell you what an entanglement is. And then you get a mixed state. And the associated inverse procedure is called purification. You purify, this is a non-unique procedure because you lose something in partial tracing, because the trace is always a many-to-one operation. You lose something and you have to edit it, this is non-unique. In my opinion, mixed states are really conveniences for saying that we don't know. I don't think there exists a mixed state. But this is another issue. So far we have been doing pure states and the resulting projection operators, which are idempotent, one-dimensional projection operators, and this is what we really need most. Yeah, we need pure states and projection operators.
Yes, a question. I understand that according to statistical mechanics, you have to introduce the density bench because the real impossibility to know all the pure state or the state of the system. So you have some statistical interpretation of of the system, and then
I
that's the
think-
reason that you have to introduce this matrix. Otherwise, you can always work with the state of the system.
No, you are always have a matrix, because even in this case here, this is a matrix.
But if you have all the information about the system,
Yeah, in a pure state, you have a kind of, it's maximally determined. Yes, yes. You know, this is a source of confusion I experience with myself and with newcomers. You have to differentiate between coherent superposition in terms of a certain basis. You know, if you have a coherent superposition like this, in terms of that basis, this is indeterminate. Yeah, because if you measure it, you sometimes get a click in this. You sometimes get the answer that it's in state 0 or in state 1. But you can have total determinism in that respect, that if you get rid of this basis.
That's very conceptual, right?
And yeah, and get another basis. There is total knowledge, because you always get this outcome here. Let's call it 0 prime. And you never get this 1 prime. Here you get a 50-50 mixture, a fair mixture. Yeah? So these are all pure states. So if you measure a pure state with respect to an improper basis, you also get. You know, and with your Marcus Heisenberg uncertainty, you cannot have it both ways. You cannot, in quantum mechanics, in classical mechanics, you always have the certainty that whatever you measure, as long as you can measure it, it's clear. Here, it's not. This is clear. If you measure in this basis, you will always get one answer. But if you measure in this basis, you get insecure answers. And some of the quantum postulates is that for simple outcomes, you get totally indeterministic answers. But this is just because you ask the wrong question. If you would ask this question, you would get a deterministic answer. But so this is still pure states. And then you have the mixed states. The mixed states is rather your knowledge about this. So you decide to look the other way, not to know anything. No? Professor Specker called this Jesuit lies. Should be very interesting here, because the Jesuits have some hearing on the States still. But also in Austria, of course. You just pretend, you know, because you're tortured by some people, and you should not tell a lie. So you say, you look the other way, say something. The brother is somewhere else. You look and say, no, he's gone there. Whereas if you look the other way. Anyway, so in a mixed state, this is not a mixed state perspective.
yeah.
And then, probably we should do this before, and then there is still another source of confusion, that's an entangled state. Now, an entangled state is a pure, let's say, can be also non-pure, but let's talk about pure entangled state. An entangled state is something like a 50-50 mixture, but not a mixed state, yeah? Of multipartite states. Let's say 0, 0 plus 1, 1. Yeah? So if you have two particles, you have to normalize that. And they have a specific property. So just absorb, please, that I claim that I will shortly show formally, defined formally, and by the way, you can read this in Merlin as first chapter, I think, as this argument I'm going to present to you in a second. There is a superposition. The superposition is this here in terms of this basis. Then you get a mixed state. A mixed state means that the trace is 1, but it's not a projection any longer, so it's not idempotent. Okay? And then the new notion is an entangled state. And let's only talk about entangled pure states. So if you have a two-particle state, let's say a two-particle state such that every particle can be in one of two states, 0 and 1. So the most general two-particle state would be alpha 0, 0, 0, plus alpha 0, 1, 0, 1, plus alpha 1, 0, 1, 0, plus alpha 1, 1, 1, 1. What is this? This is here a composition of 0 and 0. With these brackets turning to the right, both. So it's a cat, bracket. Yeah. I always remember it that way. Or you write a C here and you have a bra indicator. This is just a mem-notation feature of the bracket notation. How to memorize that this is a cat. And let's say if this here is 1, 0, and this here is 1, 0, you can formally introduce a product, also a direct product, such that everything here gets in here and here. So you have 1, 0 from the first bit, and then you have a 1, 0 and a 1, 0 from the second bit, and you get a 1, 0, 0, 0. Okay? So the most general thing is alpha 0, 0 times 1, 0, 0, 0 plus alpha, well, what is this here? This here is a 0, 1. 0 is 1, 0, and the 1 is 0, 1, 0, 1. So this makes, excuse me that I use the white, on this white marker, you get a 0 here, a 1 here, a 0 here, and a 0 here. Yeah, because 1 times 0 is 0, 1 times 1 is 1, and 0 times anything is 0. So you get here 0, 1, plus and so on, the same. So you basically get an alpha 0, 0, alpha 0, 1, alpha 1, 0, alpha 1, 1. This is the most general two-particle state composed out of two particles. Two-particle states composed out of two particles. Now, one could ask, can I generate this state, the most general state, by multiplying two one-particle states? So, I need more space. but let's say I attempt to construct a psi bar by saying this is A1, no, A0, 0 plus A1, 1 times B0, 0 times B1, 1. Okay? Fair enough? So I multiply that, that's A0, B0, 0, 0 plus A1, B0, 1, 0 plus and so on. Okay? And then I compare the coefficients. I compare, because this is just standing in front of the 0, 0. So in order to, if I claim when are these identical? And can I generate all of them? So I identify A0, B0 with alpha 0, 0. I identify alpha 0, B1 with alpha 0, 1. I identify alpha 1, B0 with alpha 1, 0 and alpha, no, I'm sorry. The alpha should be A. In A1, B1 with alpha 1, 1. Okay? Fair enough? Yeah? I just do the coefficients and compare this. And if this should be left, these 4 equations will work. Now this contains still here this contains alpha 0 and alpha 1. Now if I can divide this and this cancels out. And I get B0 from this I get B0 over B1 equals to alpha 0, 0 over alpha 0, 1. Okay? And from this I get the same. B0 over B1 equals alpha 1, 0, alpha 1, 1. So basically I get alpha 0, 0 over alpha 0, 1 equals to alpha 1, 0 over alpha 1, 1. Yeah? It's simple. Yeah, it's just a division. If I can. So basically I get that if this is true, alpha 0, 0 times alpha 1, 1 equals to alpha 0, 1 times alpha 1, 0. Yeah? So the coefficients of this product state gives you all states with whose general coefficients should obey these ones. But these are just product states. Now I define the following thing. An entangled state of two particles is one with the property that this is not the case. It's not the case that it's a product state. And you say, well, what is it? Give me an example. And the most common example is the so-called Bell state, which is part of the Bell basis. I'm looking for a place to squeeze this still in, and the Bell state is this one. It's psi minus, and Professor Vrije will speak a lot of this tomorrow. Lunchtime now, okay. Just a second. Okay. 1 over square root of 2. 0, 0, 1 minus 1, 0. Now, what is the coefficients of this state? The coefficients of this state, if you compare them with alpha 0, 0 equals alpha 1, 1 equals what? I'm sorry, in Vienna University, I always ask students, but they are shocked because yes, this is 0. And alpha 0, 1 equals minus alpha 1, 0 equals 1 over square root of 2. And if you look at this in here, this gives you 0, and this gives you 1/2. So this is an entangled state of two particles. Entangled means it cannot be written as a product. So and just before the break, I will give you this message, 2 messages. This is amazing, because in quantum mechanics, there exist states by definition, which cannot be formed by the product of 2 individual states. This has been introduced by Schrödinger in the context of measurement, and he very clearly says this, and many people have not realized that basically Schrödinger said already, you cannot have it both ways. You can, if you have 2 particles, this is of course only a property of multipartite systems. So let's say 2 particles. These 2 particles still easy. You can have individuality sitting on the particles. You can have individual properties. And then you have a product. Or you can have relational properties. Like this one here, this thing here. You know that, let's say, if this is horizontal and vertical polarization, if you measure one particle horizontal, the other will be vertical. Or vice versa, one particle vertical, the other will be horizontal. So it's just the other way around. You know, very much the same. The Bell basis is spent by this one and by such. Here, these are the same. So this is a relational property. The relational properties is defined. So it's among them. Yeah. So this is the gist of entanglement. The gist, in my opinion. But whatever anybody else will tell you, I think I hold the truth and nothing but the truth. This is what I believe. And this is what many people from Schrödinger on. Zeilinger was the last. He said, if you read a paper that's called the foundational principle, he just rediscovered what Schrödinger has written. He says, you can have individuality on the particles, or you can have relational properties. You are free to choose, but you cannot have both. Yeah? And this is the positive side, the mystic side. The non-mystic side is that in terms of unitary transformations, this is just a vector, you know? This vector here is a simple vector, it's a pure state, and this corresponds to the vector. It's 1 over 2, and here, this is 0, 1, minus 1, 0. Yeah? Because this one here is just 0, 1, 0, 0, and this is 0, 0, 1, 0. The minus makes the minus 0. So this is the base state. It's a vector, it's a pure state. Yeah? And by rotation, orthogonal transformation, it's easy to rotate that orthogonal transformation into 1, 0, 0, 0, which is pure. So, pure states and entangled states are just a rotation away. But this rotation will not be local on the single particles. It has to be local. Okay. So, yeah.
Just one question. What's the included meaning of the physical meaning of the product? Is not product to
That's the individual particle has. I mean, this thing here. The physical meaning is two particles. One particle is in state 0 and the other is in state 1.
That one, okay, it's the same one that when you multiply these two pieces. No, the cross with the circle.
Yeah. This is just a way of writing it. It's a product.
Okay.
It's a tensor.
Okay.
So you see, this is just a coherent superposition with two particle states. So this is how a coherent superposition again in the multipartite regime gives you another weird property. You know, the coherent superposition already is weird due to Schrödinger cat and jellification and whatever. But in multipartite it's even worse. It says that single particles have no definite value. You shift all the information because it's a zero-sum game, and I can tell you next term why it's a zero-sum game, because it's just rotations. It's just permutations. We are just permuting the state. There's nothing lost and nothing gained. Yeah? So it must be a zero-sum game. You just permute the individual information onto the relational properties, onto the joint state. You are recoding it, scrambling it. And you can descramble it. You can go back. I've invented a series of projections where you rotate into the Cartesian basis, belt basis, Cartesian basis, belt basis. You can do that 4 times.
I have another question.
Yeah.
When you were talking about the double split experiment, I know that the way the double split experiment, I know that the wave function goes, then after the split, we have 2 wave functions that the square root of the sum creates the interference pattern.
It's only one wave function.
Yeah, it's still
has 2
one.
components.
Yeah, but how formally you describe the generating of the 2 parts at sum? You understand it?
How to create?
How formally do you describe the transition from above and after going through the split? I never understand that part.
This is by, there is a paper by Juan Zeilinger.
I understand the consequence and I understand why it is.
Yeah, you're talking.
Because you must go to lunch very quickly.
Ah.
You will not have enough time.
Okay.
It is a long answer. Maybe you can solve the lunch. Sorry.
No, but the short answer is this. You have, this is the first slit, this is the second slit. Yeah? And they always tell you A goes into B plus E because of the reflection. This is a reflection phase, whatever the phase is, I just say it's C. So this is the double slit kind of. And there exists a paper by Juan Zeilinger and Greenberg in Science.
I have some information very briefly. Sorry to kill the physics and mathematics fun. I'm Simon Palacios. I'm coordinating with Tomas and his little helper. So Tomas have sent you all, I have heard, some mails with restaurants that are very near from here. They are that way. I'm gonna show you there is a Peruvian here and there is a Chinese restaurant over there. So that's the recommendation that you are free to choose. And if you need some certification, you can approach Thomas later, or you can approach Evelyn, who is in the table, and you can ask the certification. And Thomas is going to make a course, a class, and he will return to the next several courses, classes here in the afternoon. And we're gonna start meeting here at, it was 2:45. That's the idea. That's the ideal, let's say that. And the class will start at 15 hours, so 3. Okay? And sorry to interrupt. Professor, I have left you back in the Thomas office. Okay? Thank you.